Greetings, AP Chemistry students. Today we're going to be starting Unit 3, which is the biggest unit in AP Chemistry as far as a single unit that we're going to consider. It also makes up over 20% of the multiple choice questions on the entire AP exam. Just this one unit out of 9 units, it's 20% of the AP exam questions, but it covers a whole bunch of stuff. So we start with intermolecular forces and properties, and then we're going to apply that to a whole bunch of different things, and we're going to kind of weave through a variety of different topics on our way to the end of this unit. So be prepared for that. So intermolecular forces are forces between molecules or between particles. And the stronger your intermolecular forces, the higher the melting and boiling points and the lower the vapor pressure, because you're going to have to put more energy into it to break those attractions and cause the solid to stop being attracted to itself in the rigid crystalline structure, or the liquid to stop being attracted so that it breaks apart completely into a gas. And vapor pressure is essentially the pressure of the vapor above its own liquid in a container. So the more easily you evaporate, the higher your vapor pressure. So the weakest type of intermolecular force is London dispersion forces, or just London forces or dispersion forces. If you ever hear somebody refer to these as van der Waals forces, do not use that term in AP chemistry. The College Board will not accept that term on the exam. This is an induced dipole-dipole force that causes attraction between molecules. For nonpolar molecules, this is the only intermolecular force that they have. And in large molecules, it's often the strongest intermolecular force because it's the larger the electron clouds and the larger the molecule, the easier it is to induce dipoles, because this forms by temporary shifts in the electron density within an atom or a molecule. And there's a term called polarizability. And whenever you're discussing this, the term polarizability is a good term to put into your free response as long as you use it correctly. Polarizability is the ability to form an induced dipole. And something is more polarizable the larger its electron cloud. And that's because the more loosely held the electrons are, which is true the further away they are from the nucleus, the more easily the dipoles are induced. So the more easily you can get this temporary shift in electron density. So for instance, something like candle wax, which only has London dispersion forces, it's still a solid at room temperature because candle wax molecules are absolutely massive. I mean, they're many dozens of carbon atoms long with a bunch of hydrogen. So these huge molecules can form lots of London dispersion forces with each other to still hold them together as a solid, even though it's the weakest of the intermolecular forces. So this kind of shows how this whole process happens with atoms. For instance, if you bring them close together, you could get this temporary shift in electron density, which then induces a shift in electron density on the other atom, so that you end up with a negative side and a positive side, and they're attracted to each other. In molecules, this could also happen. So this atom A and atom B over here, that's an example of, say, a noble gas. But you have to get them really, really, really cold before you can ever get these attractions to become significant enough to make them a liquid or solid. So the next force is dipole-dipole forces, which are attractive or repulsive, depending on the orientation. Forces between polar molecules, the ones with permanent dipoles in the molecule. The ones that we learned last unit are polar molecules. Dipole-dipole forces are stronger than dispersion forces, and their strength depends on the magnitude of the dipoles. The greater the difference in electron density within the molecule, the more polar the molecule, the greater the dipole-dipole forces. Then there's another force called dipole-induced dipole forces, which is the attractive force between a polar molecule and a nonpolar molecule. Because if you bring a polar molecule up to a nonpolar molecule, it can induce a temporary dipole in that nonpolar molecule. For instance, the positive end of a polar molecule coming up to a nonpolar molecule can pull the electron density towards it and set up an induced dipole. Now, this is more likely to happen the more polar the one molecule you have and the more polarizable the other molecule is. So, molecules with large electron clouds and then other very polar molecules, you're likely to get this to happen. Then there's what's called ion dipole forces, which are attractive forces between ions and polar molecules such as water. So, for instance, when a salt dissolves in water, like for instance, sodium chloride, you have the positive sodium ions are being surrounded by the negative ends of the polar water molecules, and the negative chloride ions are being surrounded by the positive polar ends of the water molecules. And those attractions are called ion dipole forces. And these are pretty significant in order for molecules to dissolve. And obviously, the greater the value of charge, the greater the polarity. Coulomb's law all fits in with this. And ion dipole forces are quite strong because you're working with something that's got a dipole on it, plus you're working with something that's just got a straight up either positive or negative charge. You're going to have pretty strong attractions going on there because you're not going to have as many opportunities for repulsions happening. This right here shows dipole-dipole forces as they're taking place. And then there is the strongest intermolecular force of all, which is often the most misunderstood, hydrogen bonding. Hydrogen bonding exists when hydrogen atoms covalently bonded to a nitrogen, oxygen, or fluorine are then attracted to the negative end of a dipole formed by another nitrogen, oxygen, or fluorine in either the same or a different molecule. So this happens because if you think about the hydrogen atom, it's just a proton and an electron. And if hydrogen is bonded with nitrogen, oxygen, or fluorine, those are extremely electronegative and rather small molecules. So based off Coulomb's law and the electronegativity, they're going to pull the electron that hydrogen has very close to the nitrogen, oxygen, or fluorine. So that all you have hanging off the end of the molecule where the hydrogen is basically a naked proton. There's nothing else around it. The electron is over more with the nitrogen, oxygen, or fluorine. Also, when they form compounds, nitrogen, oxygen, or fluorine, they have lone pairs of electrons on them, which can attract those naked hydrogen atoms on another molecule where this is also occurring. Because of hydrogen bonding, water, despite being a very small, lightweight molecule, is a liquid at room temperature. And it's only got a molar mass of 18 grams per mole, whereas carbon dioxide at 44 grams per mole is a gas. The key compounds where hydrogen bonding occurs are hydrogen fluoride or hydrofluoric acid, NH3 or ammonia, and water. Those are the most common ones that you think of. But hydrogen bonds are also what bind adenine to thymine or uracil and guanine to cytosine in DNA and RNA. So this kind of shows how you've got the positive and negative ends of water molecules, and they can form hydrogen bonds between the hydrogen on one molecule and the oxygen on another. Now, what makes water have these extremely strong attractions is because it has two hydrogens capable of hydrogen bonding, and it has two lone pairs of electrons on the oxygens that can accept hydrogen bonds. So each water molecule can be hydrogen bonded to 4 other water molecules, which makes it much stronger than in, for instance, hydrogen fluoride, where the fluorine can accept 3 hydrogen bonds, but it only has 1 hydrogen to form them, or NH3 ammonia, which can form 3 hydrogen bonds with the hydrogens, but the nitrogen only has 1 lone pair of electrons. However, if you mix them with each other, you could get some really strong attractions, or with water. Those things are all extremely soluble in water. And then this shows how adenine and thymine, they will form two hydrogen bonds with each other. And then you have guanine and cytosine, they form three hydrogen bonds with each other. And they always pair up in a very specific order. You can't mix and match these. That's why A's always pair up with T's and G's always pair up with C's in DNA and RNA. It kind of assembles itself. So essentially, when you go to DNA replication, DNA helicase goes through and it breaks these hydrogen bonds and essentially unravels the molecule. And then some of these base pairs are floating around free within the nucleus, and they'll come in and pair up. And this whole thing, basically, the replication process essentially happens automatically because of the hydrogen bonding. It's like a self assembling magnetic puzzle, if you will. Now, this also shows the significance of hydrogen bonding on some boiling points. So, for instance, the elements in group 14, the carbon group, there's no hydrogen bonding with any of these. With group 15, the nitrogen group, NH3 has a higher boiling point than PH3 or the phosphorus trihydride or arsenic trihydride because it can form hydrogen bonds. In group 17, hydrogen fluoride has a much higher boiling point than hydrogen chloride, hydrogen bromide, or hydrogen iodide because it can do hydrogen bonding, whereas these just have dipole-dipole forces. And then water, with its ability to form two hydrogen bonds, much stronger still. It's got the highest boiling point of them all at 100 degrees Celsius. Carbon tetrahydride, or methane down here, it's got a very low boiling point because it's not only does it not have hydrogen bonding, it's nonpolar. So it doesn't even have dipole-dipole forces helping hold it together. It's very weakly attracted to other CH4 molecules, and methane or natural gas, it very easily turns into a gas. I just want to discuss a few things with you to help you be prepared for what's coming in the next few days. So, the first thing is talking about intermolecular forces and polar versus nonpolar molecules. A key thing for you to note is that although everything has dispersion forces, London dispersion forces, and there are dipole-induced dipole forces between a polar molecule and a nonpolar molecule. Since dipole-dipole forces are so incredibly strong, and when you come to water molecules, hydrogen bonding is so incredibly strong, it leads to some interesting effects when you mix a polar substance with a nonpolar substance, such as when you mix oil with water. Because the oil has dispersion forces with itself, London dispersion forces, and it can also have London dispersion forces and dipole-induced dipole forces with water. But because water is so polar and can form those strong hydrogen bonds with other water molecules, when you try to mix oil and water, it's not that the water molecules are repelled from the oil. It's not that oil and water repel each other. It's just that water is really attracted to itself. And so it attracts to itself and pulls itself together. And so the oil just gets kind of left out. And because it's less dense, it floats up to the top. So I'm going to show you a quick video demonstration of that right now. In this jar is a mixture of oil and water. Notice the oil is on top of the water because oil is less dense than water. And the water, I've added some red food coloring to help you see the difference. Now if I shake it up, what you might notice is that the oil droplets and the water droplets, the oil literally gets squeezed out of the water. As the water molecules come together and form those hydrogen bond interactions with each other, it literally squeezes out the oil, which is why you end up with those little bubbles of oil. There's water droplets trying to squeeze it out, and that's why ultimately it ends up separating back out. Is the water molecules are more attracted to themselves than they are to the oil.